Welcome to The Explainer. Today, we are going deep inside the atom to figure out what gives it its personality. I mean, have you ever wondered why one element is super reactive while another just kind of keeps to itself? Well, it all boils down to a few simple fundamental rules.
So, let's start with a little mystery. What is it that gives a lemon its signature sour tang? Or what makes table salt, well, salty? The answer isn't something you can see on the surface. Nope, for this, we've got to zoom way in, down to the level of individual atoms and see how they act.
All right, to get to the bottom of that mystery, we have to start with the basics. Let's first get a handle on what gives an atom its fundamental identity in the first place. Okay, so what's an atom even made of? What are the tiny little building blocks that create this miniature universe and end up dictating so much about our physical world?
Well, every atom has three key players on its team. Right in the middle, in the nucleus, you've got your positively charged protons and your neutral neutrons. And then buzzing around that core, you have the negatively charged electrons. The dance between these three particles, that's where all the magic begins.
And here's where it gets really simple and kind of beautiful. An atom's entire identity, what makes it what it is, comes down to just one number: how many protons it has. If an atom has 8 protons, it's always oxygen. If it has 6, it's always carbon. It is the unchangeable fingerprint of that element.
But nature always has a few variations up its sleeve. Let me introduce you to isotopes. Think of them as siblings. They're the same element, so they have the exact same number of protons, but they carry a different number of neutrons. Take hydrogen. Most have 0 neutrons, but if you add 1, it becomes deuterium. Add 2, you get tritium. Same element, just a little heavier.
Okay, so while the protons give an atom its name, it's the electrons that give it its personality. The electrons are the ones that decide how an atom is going to interact and behave out in the chemical world.
So, how exactly do these electrons arrange themselves? It's not just some chaotic cloud flying around. No way. They follow a really strict set of rules, living in specific energy levels, or what we call shells, at different distances from the center.
And believe it or not, these strict rules can be described by a really simple and elegant formula, 2n squared. In this case, n is just the shell number, starting with 1 for the one closest to the nucleus. This little formula tells you the absolute maximum number of electrons that can fit in any shell, and that is everything.
Let's just put it into practice. For that first shell, where n equals 1, the formula tells us you can have a max of 2 electrons. For the second shell, where n is 2, it can hold up to 8. And the third, up to 18. This super orderly filling system is the real key to understanding why atoms bond the way they do.
So, if you remember one thing, make it this. An atom's #1 goal in life is to get its outermost electron shell completely full. That's when it's most stable, most content. This single motivation, this universal quest for a full shell, drives pretty much all of chemistry.
Now, this powerful drive for stability forces atoms to make a big choice. Should I gain, lose, or share electrons? And that very choice is what can transform a neutral atom into a charged particle, completely changing its nature.
So what happens if you're an atom and you're not stable? What if your outer shell is almost empty? Or maybe it's just 1 electron away from being full? What's the easiest path to that stable, happy place?
Let's take a look at a real-world example. Sodium. It has 11 electrons. So if we follow our rules, 2 go in the first shell, 8 fill up the second, and that leaves just 1 single lonely electron way out in the third shell. This is a very unstable, very unhappy atom.
So, sodium has a choice. It could try to find and grab 7 more electrons to fill that outer shell, which is a ton of work. Or it could just get rid of that 1 lonely electron. Yeah, it's way easier to just give away that 1 electron. And when it does, its new outer shell, that second one, is perfectly full.
But here's the catch. By losing a negative electron, that sodium atom isn't neutral anymore. See, it still has its 11 positive protons, but now it only has 10 negative electrons. That imbalance gives it an overall positive charge, and it's officially become a charged particle, what we call an ion.
And this process basically creates 2 kinds of ions. Cations are the positive ones, like our buddy sodium, that are formed when an atom loses electrons. Little tip, think of the T in cation as a little plus sign. On the flip side, anions are the negative ions, formed when an atom gains an electron from somewhere else. This whole give and take is the basis for how so many things are held together. Okay, so let's bring this all the way back around. How does this whole idea of forming ions explain that sour taste we were wondering about at the very beginning?
Well, the classic definition of an acid is actually beautifully simple. It's just any substance that, when you dissolve it in water, releases hydrogen ions. A hydrogen atom is just one proton and one electron, right? So when it loses that electron to become an ion, all that's left is basically a bare proton, the H+ ion.
And there it is, the secret to the lemon's sourness. It is literally just the high concentration of these free-floating H+ ions in the juice interacting with your taste buds. And that very same ion is what allows us to do a quick chemical test to see if something is an acid.
You've probably seen this classic lab procedure before, the litmus test. You just take a strip of blue litmus paper, dip it into the liquid, and if those H+ ions are hanging around, they cause a chemical reaction that turns the paper red. It's a direct, visual confirmation that, yep, you're dealing with an acid.
So let's just recap our whole journey here. We started in the nucleus, where protons define the element. Then we moved to the electron shells, where that constant quest for stability dictates the atom's entire personality. That quest creates charged ions, and it's those ions that are responsible for the real, tangible properties we experience every single day, like acidity.
And that really brings us to a final, pretty big thought. If this one fundamental drive for a full outer shell can explain something as common as taste, what else can it explain? The energy in a battery, the saltiness of the ocean. It turns out this simple atomic game of stability is the invisible force shaping just about everything around us. Makes you wonder what other mysteries it solves, doesn't it?